So I want to now consider the question, given a very generic problem like this, how can we find lambda and how can we find the eigenfunctions? Because if you think back to how we did things with simple differential equation, phi double prime equals minus lambda phi, with very simple boundary conditions, phi of 0 equals 0, phi of 1 is equal to 0, stuff like that. How did we do it? Well, we first had the equation. We did some analysis to determine that lambda had to be non-negative or even positive. Once we knew that, we had that piece of information about lambda, then we could get a formula for the solution to the differential equation, and then we could take the boundary conditions to say, okay, lambda has to be equal to this, like k pi, or k pi squared, something like that. Okay, so for more general problems like this, that's not going to be as easy for a number of reasons. Even if we can assume that lambda is going to be greater than or equal to 0, it's going to be difficult typically to solve the differential equation. And then even once we do that, even with an easy differential equation, we could get a transcendental equation for lambda when we're trying to, when we plug in the boundary conditions here. So then usually when we do something like this, we're going to have to sort of do a numerical method to figure out what the solutions to the, to figure out what the eigenvalues and eigenfunctions are. And I just want to illustrate that in a number of ways with the following example. So we're going to look at phi double prime is equal to minus lambda phi. Sorry, I need to silence my phone. Phi double prime is equal to minus lambda phi. And then we're going to have these boundary conditions. Phi of 0 plus phi prime of 0 is equal to 0. And phi of 1 is equal to 0. And I just want to describe one method that can be used in order to try to get an idea about what the eigenvalues are. Okay, so I'm going to look at this, and I'm going to sort of ignore the boundary condition at phi of 1 for now. I'm just going to block that out of my mind. And I'm going to try to solve this. Phi of 0 plus phi prime of 0 is equal to 0. Okay, so if we think about lambda, like let's see what we can tell about lambda, sort of, is it non-negative, that sort of thing. If we think about the Rayleigh quotient for this problem, P is equal to 1, Q is equal to 0, sigma is equal to 1. So we're going to have something like this, minus phi prime. We're going to evaluate this from A to B, and then plus the integral from A to B is going to just be P. P is 1, so it's just going to be times phi prime squared. And then divided by the integral. A and B are both 0 and 1. I know what those are, so let me just place this. This is 0 to 1. And then we're going to look at 0 to 1 phi squared. So I want to compute what this is, or estimate this. Is it positive? Is it negative? Or what is it? So phi is just going to be any eigenfunction, and I want to analyze this. Okay, so something that I'm going to do that seems like maybe it shouldn't even be allowed is to, again, I'm ignoring this. Sorry, I'll do that in just a moment. The first thing that I want to do is I want to examine this right here. Sorry, it's the end of the day on a Friday. I'm a little scatterbrained here. When you plug in phi of 1, you get 0. So the boundary term corresponding to 1 is 0, and so we have 0 minus phi of 0, phi prime of 0. Now, phi prime of 0, by this boundary condition here, phi prime of 0 is equal to minus phi of 0. So it's like this. It's minus phi of 0. And we have something like this. Now, this is going to be minus, got plus here, so this is going to be minus phi of 0 squared. And then plus that. Okay, and so now, I don't know, maybe it's clear to you, but it's not so clear to me what the sign of this is going to be. So I'm going to do the following. If I do phi of 1, so I want to somehow compare this with the integral of the derivative. So if I do phi of 1, which I'm going to keep in the back of my mind is equal to 0, phi of 1 minus phi of 0 by the fundamental theorem of calculus, this is the integral from 0 to 1 of phi prime. Now, by the Cauchy-Schwarz inequality, well, I can think about this as phi prime times 1. And so by the Cauchy-Schwarz inequality, this is going to be less than or equal to the integral of 1 squared from 0 to 1, that's just 1, but times the square root of the integral from 0 to 1, phi prime squared. Now, if I square both sides, so if I just look at the outside, and if I look at this and I look at that, phi of 1 minus phi of 0 is less than or equal to that. Sorry, I keep having some minor issues. So I guess let me now, phi of 1 is equal to 0, so this gives me minus phi of 0 is less than or equal to the integral, the square root of the integral from 0 to 1 of phi prime squared. So we have something like this. Now, notice one thing that we can assume here. All we've assumed about phi is that it is an eigenfunction and it satisfies these two boundary conditions. So I can assume that the eigenfunction I'm dealing with right now, phi of 0 is negative. Why can I assume that? I can assume that because if it's positive, if phi of 0 is positive, I can multiply it by minus 1, and I get a negative function. And that's still going to satisfy the PDE or the ODE, and it's going to satisfy the two boundary conditions. If I just multiply this by minus 1, it's going to be equal to 0. If I multiply this by minus 1, it's going to be equal to 0. In addition, it can't be equal to 0. So phi of 0 can't be equal to 0, because if phi of 0 is equal to 0, well, that would go away, and that would imply phi prime of 0 is equal to 0. Well, if you have an ordinary differential equation, and phi of 0 is 0, and phi prime of 0 is 0, this implies that it's the trivial function if it's a second order differential equation. Okay, so in other words, the left-hand side, if phi of 0 is negative, then the left-hand side is positive. So I've got a positive thing here, a positive thing here. If I square it, I'm going to maintain the same inequality. And now what we have is phi squared of 0 is less than or equal to the integral from 0 to 1 of phi prime squared. So what it says then is this has to be positive because phi squared of 0 is less than or equal to that integral. Okay, and so minus that plus that has to be greater than or equal to 0. Okay, so what this tells us is that lambda has to be non-negative. Maybe there was another way to show that. I'm not sure though. This was the thought that came into my mind. I guess probably if you try some sort of assume that lambda can be negative and solve this, you're going to get an exponential, and maybe you're not going to get it to satisfy those things. Okay, so what we know then is phi of x is going to have the form a cosine square root of lambda x plus b sine square root of lambda x plus b sine square root of lambda x. If we look at the condition at 0, so now this is just I'm no longer assuming that phi prime of 0 or that phi of 0 is negative. I only needed that for the lambda. Okay, but Okay, so now I have this. Now, if I take the derivative, I'm going to get phi prime of x is equal to minus a square root of lambda sine square root of lambda x plus b square root of lambda cosine square root of lambda x. Yes, okay. And if I look at the boundary condition at 0, it says phi of 0 plus phi prime of 0 is equal to 0. So if I plug in x is equal to 0 here, I get a. If I plug in x equals 0 over here, I'm going to get plus b square root of lambda. So what this tells me is that a is equal to minus b times the square root of lambda. So I'm going to write this as minus b times the square root of lambda. Okay, so I'm ignoring the condition on 1 right now, on phi of 1 is equal to 0. Now if I look at this, I can factor out a b from both sides of this equation, but I'm not going to do that for just now. What I can do, in a problem like this, I can introduce an auxiliary condition at 0. The reason I want to do that is because I just want to be able to specify what b is. And so the auxiliary condition I'm going to introduce is going to be phi prime of 0. It's going to be phi prime of 0. Sorry, I wrote down the best one to do earlier. Sorry, it seems like I started this video an eternity ago. Phi prime of 0 is equal to 1. Right, if phi prime of 0 is equal to 0, it wouldn't make sense. Sorry. So the auxiliary condition I'm going to put is phi prime of 0 is equal to 1. Because if we think back to eigenfunctions, even once we consider both once we can consider both boundary conditions, we still have a leftover parameter. And we're going to choose to determine that parameter by setting this auxiliary condition, phi prime of 0 is equal to 1. So in other words, if I come down here, I'm going to have, so a here, what did I have here? This was minus a times square root of lambda, but remember a is equal to minus b square root of lambda. Sorry, this is inconsistent with what I have in my notes here. Sorry about that. Yes, okay. So now a, sorry, I'm doing this slightly differently than I had in my notes. I realize that now, and it's confusing me just a little bit. Sorry about that. Okay, so a is equal to minus b times the square root of lambda. So then here we're just going to have b times lambda. Okay, and phi prime of 0 is equal to 1. So what we're going to have here is 1 is equal to phi prime of 0. So if you plug in x equals 0, this goes away, and you're just left with b times the square root of lambda. So what this says is b is equal to 1 over the square root of lambda. So if we come over here, b is 1 over the square root of lambda. This is just going to be equal to minus cosine square root of lambda x, and then b is 1 over the square root of lambda. Okay, so this is the solution. This is the solution to the initial value problem with phi of 0 plus phi prime of 0 is equal to 0, and phi prime of 0 is equal to 1. What we want to do now, sort of if we think graphically, I'm going to do this in the next video. What we're going to do is we're going to take this and we're going to graph it from 0 to 1. And we're going to have this parameter square root of lambda. I'm going to have it in Desmos. And I'm going to slowly increase this parameter. And what we're going to see happen is the following. This is going to satisfy, it's going to be over here somewhere. This is 1. We're going to slowly increase lambda. and we're going to get functions whose graph looks something like this. And we increase lambda a little bit more, and the graph looks something like this. And we increase lambda a little bit more, and eventually it's going to be equal to 0 at 1. And that's going to give us an eigenvalue. And then we're going to increase lambda a little bit more, and we're going to get stuff like this. We're going to increase lambda a little bit more, get stuff like this. Increase lambda a little bit more, and finally it's going to be equal to 0 there again. That's going to give us the next eigenfunction and the next eigenvalue, and so on and so forth. And by increasing lambda this way, we can figure out what the eigenvalues are. So in other words, we're going to define a function. If this is phi of x, and I'm going to put like a comma lambda because it depends on lambda over here. What we want to define is f of lambda is equal to phi of 1 lambda. And we want to find the roots of this function. And we know how to find the roots of the function using Newton's method or something along those lines. For this method, for this example, Newton's method might be fine, or a sort of bisection method would also be fine. And but I'm not going to talk too much about the numerical stuff. I just wanted to show you graphing a few different ways that we can figure some of this stuff out. The other thing that I want to mention is very similar to this. I'm going to show you both ways, so you're going to want to write this down. If we plug in 1 and set it equal to 0, we're going to get minus cosine square root of lambda plus 1 over the square root of lambda sine square root of lambda is equal to 0. And if we move things around, if I move the cosine lambda over there and then divide, what we're going to get is tangent square root of lambda. If I add that over there, multiply by the square root of lambda, divide by the square root of, divide by cosine square root of lambda, I'm going to get tangent square root of lambda is equal to the square root of lambda. And now this is another, like I said, transcendental equation that we can solve for lambda. And I'm going to do that graphically in the next video.